So we're talking about Chapter 2, Section 6. We're talking about combining functions. So you'll take a note of the definition here when we talk about combining functions. If we let f and g be functions with domains a and b, then the following functions are defined. So if we have the sum of functions, f plus g, then what we do is we simply just take f of x and add g of x, and there's our output. And the domain of that is a intersect b. If we're looking at the difference between two functions, f minus g, we just take the first function f of x and subtract the second function g of x. Again, domain a intersects b. That is what's common between the domains of f and g. If we're looking at the product, it's just the product of f of x times g of x, and the quotient is the quotient. But one extra thing, not just a intersect b in terms of domain, we can't have the denominator equal 0. We know that we can't put any value in for x such that g of x equals 0. So I have an example here. I've defined two functions, and I want to find the sum, the difference, the product, and the quotient of those two functions. So if I want to find f plus g of x, by definition, I use f of x plus g of x. This is f of x plus g of x, which will be f of x is 1 over x minus 2 plus root x. Okay? So this is f of x plus g of x. Okay, there it is. So we got f of x, we got g of x. And there's no simplification I can do. If there is, you want to do it. In this case, there's not. What is the domain? Well, we know that the domain of this thing is you got to be greater than or equal to 0. So we have that, and we also know that in here we can't have x equal 2. So we have to be greater than or equal to 2, greater than or equal to 0, and not equal to 2. So the domain is a set of all x such that x is greater than or equal to 0, and x cannot equal 2. Right? All right, let's look at the difference now. F minus g of x, which is f of x minus g of x. So this will be 1 over x plus 2 minus root x. Turns out the same domain applies. Got to be greater than or equal to 0 here. Can't be equal to 2 here. Got to have both of those. So the set of x such that x is greater than or equal to 0 and x cannot equal 2. Okay. Let's look at the product of those two. F times g of x, which is defined to be f of x times g of x, which is just root x over x minus 2, right? This guy times this guy, top times top, bottom times bottom. Again, same story. Domain, set of x such that x is greater than or equal to 0 and x cannot equal to 2. Okay, lastly, we have the quotient. F over g of x, which is f of x divided by g of x, which is f of x is root x. We're dividing by the, f of x is 1 over x minus 2. We're dividing by root x, which is the same thing as multiplication by the reciprocals. This will be 1 over root x times x minus 2. Now, the domain changes on this one. Why does the domain change on this one? Before we had x had to be greater than or equal to 0, and also x cannot equal to 2. But in this one, we can't have x equals 0 because we can't have 0 in the denominator. So this one changes just slightly. We got to have the set of x such that x is greater than 0 and x is not equal to 2. So again, this domain changed slightly because we can't have 0 in the denominator. Okay. All right, so this is combining functions. Again, sometimes when you combine them, you will be able to simplify them because there'll be two functions that have like terms. You can add them, or maybe they have common factors on numerator and denominator. Make sure that you don't, when you cancel, you still consider those values in the domain. Okay. All right, there's one other way to combine functions that we're going to talk about, and that is composition of functions. So we have some difference, product and quotient. Let's talk about composition of functions, and this is the hardest one. So given two functions f and g, the composition is f composed with g. That is not spelled fog. Okay, this is f composed with g, and it's defined by this rule. And this, the way this is read is f of g of x. So f of g of x, that's kind of read of, f of g of x equals f of g of x. Okay, and that's the rule that we're going to use. Now, to understand the domain of this stuff, let's understand that the domain of this function, this composition function, is the set of x that have the property that g of x is are in the domain of f. So the domain of this function is the set of x's in the domain of g, such that the g of x's are in the domain of f. Okay? So let's use this rule over here. I have two functions, f of x equals x squared, I have g of x equals x minus 4. Let's find f of g, f composed of g. Well, note that this equals, according to our rule, f of g of x, which is equal to f of g of x, f of g of x. F of 3 is 3 squared, f of 9 is 9 squared, f of 10 is 10 squared. F of stuff is stuff squared. F of stuff is stuff squared. F of stuff is stuff squared. What's stuff in this case? Well, my stuff is g of x. So I want to put g of x right here. Well, what's g of x? X minus 4. So g of x is x minus 4. F of stuff is stuff squared. F of stuff, what's stuff? X minus 4. X minus 4 squared. If I multiply this out, I get x squared minus 8x plus 16. So f of g of x turns out to be x squared minus 8x plus 16. Let's do g of f. Okay? Well, according to this rule, g of f equals g of f of x. Okay? So this will be g of f of x. Well, g of stuff is stuff minus 4. G of 9 is 9 minus 4. G of 10 is 10 minus 4. G of anything is anything minus 4. This is g of anything is anything minus 4. What's my anything in this case? It's f of x. What's f of x? X squared. So the answer is x squared minus 4. Now you'll note something. Is f of g of x equal to g of f of x? In other words, are these two things the same? And the answer is no. So it is not always true that f of g of x equals g of f of x. This is not always true. Okay, so it's not always true. I mean, it's true if I had f of x plus g of x, I get g of x plus f of x. 5 plus 3 is 3 plus 5. 9 times 3 is 3 times, what is it? 9 times 3 is 3 times 9. But when you compose two functions, it's not true that they're commutative, that f of g is g of f. Okay, and it's very important. You can tell by looking at this example here. Now, given f of x equals 3x minus 5, and g of x equals 2 minus x squared, I want to find the following. First one is I want to find g of f of 0. Well, what is g of f of 0? Well, the first thing you do inside with this parentheses first, what is f of 0? Well, f of 0 equals 3 times 0 minus 5, which is 0 minus 5, that's negative 5. So really I'm looking for g of negative 5 because f of 0 is negative 5. And then what's g of negative 5? G of negative 5 is 2 minus negative 5 squared, so 2 minus 25, which is negative 23. Okay? What about f of negative 1? So first I find f inside here, just find this part first. F of negative 1 is 3 times negative 1, which is negative 3 minus 5 is negative 8. So really I'm looking for f of negative 8. Inside here, what's inside here, f of negative 1 is negative 8. If I put in negative 1 in here, I get negative 8. So I'm looking for f of negative 8. That was negative 8. Well, what's f of negative 8? Well, it's 3 times negative 8 minus 5, which is negative 24, minus 5 is negative 29. Okay. What about g of 2? So first you find g of 2. G of 2 is 2 minus 2 squared, which is 2 minus 4, which is negative 2. So I'm really looking for g of negative 2. Well, what's g of negative 2 then? Well, g of negative 2 is 2 minus negative 2 squared is 4. So 2 minus 4 is negative 2. Okay? Here we got to write out one step. F of g of x, or f of g of negative 2, is f of g of negative 2. What's g of negative 2? G of negative 2 is 2 minus negative 2 squared. Negative 2 squared is 4. 2 minus 4 is negative 2. So really I'm looking for f of negative 2. Well, what's f of negative 2? 3 times negative 2 is negative 6 minus 5 is negative 11. Okay. What about g of 3? This is g of 3. First got to find g of 3 first, correct? Because then we're going to write g of whatever that turns out to be. Well, g of 3 is 2 minus 3 squared, so 2 minus 9 is negative 7. I'm looking for g of negative 7. G of negative 7 is 2 minus negative 7 squared, 49. 2 minus 49 is negative 47. Okay, so this is using compositions of functions and working through them. Now we're going to look at this graphically now. Okay, so now we're going to talk, given graphically define two functions. I've got g, the red one, and f, the blue one here. I want to talk about the composition of functions here. Suppose I want g of 3. Well, by rule, this is going to equal g of 3. Now, what's g of 3? G of 3 is the height of the red function at 0. Actually, at 3. 1, 2, 3. Here's x3. What's the height? 0. So really, since g of 3 is 0, I'm looking for g of 0. Well, g of 0 is the height of the red function at 0. What's the height of the red function at 0? It looks like it's about 1/2. So this will equal 1/2 here. Okay. Try the next one. F of g of 2. So this will be f of g of 2. Well, that's going to be f of, well, what's g of 2? G of 2 is the red function, right? We're looking for the red function at x equals 2. How high is the red function at 2? Well, it's too high. So really I'm looking for f of 2. Well, how high is the blue function at 2? Well, here's the blue function. How high is that at 2? Negative 2. Okay. Here we used our definition. This is equal to g of f of 2. Again, how high is the blue function at 2? Well, it's negative 2. So I'm looking at g of negative 2. But how high, when x is negative 2, how high is g? 2. Okay. Next one, f of 4. So f of 4. Well, what's f of 4? F of 4 is 1, 2, 3, 4. How high is that? Looks like it's 3. So therefore, what's f of 3? 1, 2, 3. How high is it here, the blue one? Well, it's 2. And then finally, f of g of negative 2. Well, g of negative 2 is the red function at negative 2. How high is it? 2. So I'm looking for f of 2. So what's f of 2? Well, what's the height of the blue function when x equals 2? Negative 2. Okay? So that's using composition of functions within a graph to find their outputs.